So in this video, we're going to go over something called exponential functions, and specifically as they pertain to growth exponential functions. And we're going to do some real-life examples just so you can see how these work. Now, I wrote the exponential function a little bit differently here. I put y is equal to a times the quantity 1 plus r raised to the t. I want to compare that to an earlier video I showed you where it was just a simple standard exponential equation, or again function. And the one I gave you there was y was equal to b to the x. Okay? And I want to show you how this and this are really exactly the same thing, but with slightly different letters, you know, just to indicate, for example, what they letters usually mean. Let's go back up here and let's do some definition of terms, okay? So again, remember that y is the same thing as f of x, and that's where we get the word function, okay? So these are exactly the same thing. So that's one thing to remember. So if you see this, just think of f of x is equal to this, okay? Another thing to know, a is what they call the initial amount of whatever substance you are starting with, whether it be money, number of bacteria, pennies, whatever. So A is the initial amount. Remember that initial means whatever you're starting with, okay? The R is the rate. The rate. Now, in this case, remember I said that the rate is, well, I didn't say it yet, but rate is percentages. So for example, if I said something like the amount of bacteria increases 15% every hour, okay? So the rate would be 15% per hour, okay? So this rate is going to be expressed using percentages. And if I said doubled, let's say the bacteria doubles every hour. So double means 100% growth. 100% would be a percentage of 1.0, okay? Now the R is always expressed as a decimal, okay, in this particular example. Now the T is time. And you can make that time anything you want. You can make it hours, days, or whatever. But also the T is also the x. And then you can start to see how this equation rather and this equation are starting to look pretty much the same. Okay? So why are these two equations, two forms of the equation, the same thing? So the y is the y, that's just the f of x. Okay? Now, there is a number in front of the b, which we'll call a coefficient, and sometimes you'll see this expressed as ab to the x. Now, this form of the equation is called the parent function. Okay? So if you are ever asked what the parent function is, it's just y is equal to b to the x. The base, which is some constant number raised to the x exponent or power. Okay, that's called the parent function. So this is just a variation of that. All right. Now, let's keep going. The 1 plus r, or the base, is pretty much this number right here. Okay? Now, there are some conditions with b. b cannot equal just 1, right? So that's why we always are adding something to that. So you could say increases or decreases at a certain rate, but it's 1 plus or 1 minus. So it can't equal just 1, and b has to be greater than 0. Okay? So it can't be negative. It cannot be a negative number. Okay, so that's just another condition for you. And then finally, remember that the x is equal to some time in this particular example, or just t. And again, you can decide whether you want the increments to be hours, days, that sort of thing. Okay? Let's take a real life example now. So we're going to take this form and use this form for this next example. Let me give you an example here. I think I might have given this particular question in an earlier video, but I'm just going to show you how it works, okay, using this equation. Y was equal to a times 1 plus r raised to the t power. Now, suppose your allowance starts with 1 penny, okay? But it would double every day for 2 weeks. All right. What would your allowance be on that last day, 14 days later? You can do this a couple of ways. You can actually just do a t-chart, right? Just like this. X and Y. You start with 1, double it, you'd go to 2. You start with 2, double it, you would go to 4. You'd start with 4, double it, you would go to what, 8, etc., etc. And then you could just graph this, right? And then you just go all the way up to day 14. Oh, did I say 4? I'm sorry, it should have been 3. If your X was 3. 1 second on that. There we go. That should have been 3, yet your amount still doubled, so you still would have 8. So that part was still okay, etc., etc. Just graph it, and you'd be able to predict it, right? The other way to do it is to put it into this equation. So let's see what that would look like. So I would say my initial amount, remember, was 1 penny. So I'm just reading this, and I'd say just 1 cent. All right? And then the rate doubles every day. So remember that doubles just means 100%. And you change 100% to decimal form, it would just be 1. So I'm just going to add another 1 for this r. And then the time, or the x, would be per day. Okay, so x is equal to day. So I just put the x up there. And look what this becomes. This becomes 1 plus 1 is 2 to the x. And when you times anything by 1, you just get that. So y would be equal to 2 to the x. Doesn't that look like the parent function? And it does. Remember, y is equal to b to the x. B is some constant, x is some time, and then y is what you finally get. So let's go ahead and put the number in for the x. We said, what would your allowance be on the last day, 14 days later? So what I'm going to do here, let me just put this up here like this, because remember, I'm just telling a story here, and I'm just going to put in 14 for the x. So I'm going to say y, which is going to be my final allowance 14 days later, is going to be equal to 2 to the 14th power. Now, if I just go over here, let's clear this off, and I'm going to say 2, whoops, turned on, 2 raised to the 14th power. Where is it? There it is. To the 14th power. 16384. So on day 14, I would have 16,384 pennies, or $163.84 for that allowance. Okay? So again, just use, as a recap, just use this form of the equation, which remember is the same thing as the parent function form for an exponential, y is equal to b to the x, with some, some changes here, so the coefficient, and then we're just breaking out the b to this number. And then remember the t, the time, is really just the x. Okay, you should be able to apply it to just about any equation or any situation you'd like for any type of growth function. I hope that was helpful to you.